Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we're going to investigate how will MH370 be found. MH370 disappeared 12 years ago. How did MH370 disappear into the southern Indian Ocean? How can a modern aircraft like a Boeing 777 simply disappear? In the modern global glasshouse of radar and satellite systems, surely someone must have tracked the aircraft. Questions have been raised regarding potential detection by over-the-horizon radar, underwater acoustic systems, and military radar installations. A lot of questions and few answers. Independent aircraft investigations brings you the established facts. We provide traceability of all evidence to a source authority. We make a clear distinction between factual data and analytical interpretation. If you find this analysis useful and want to see future independent investigations, then subscribing to the channel helps ensure this work continues. This episode does not prove intent, motive, or final causal conclusions. Where interpretation is presented, it is identified as analytical inference and remains subject to revision as new evidence emerges. Aviation news is covered on Daily Airline News with Jeffrey Thomas, as it happens. This channel is reserved exclusively for in-depth investigations. So, where is MH370? MH370 likely lies somewhere in one of the most remote, deepest, and least mapped ocean regions on Earth, and the available flight path data is not precise enough to pinpoint the wreckage. The disappearance of Malaysia Airlines Flight 370 remains one of aviation's biggest mysteries. Despite massive search efforts, several factors make it extremely difficult to locate the aircraft. Here are the main reasons. The search area is enormous. Secondly, the ocean is extremely deep and the seafloor is rugged. Thirdly, the aircraft may be broken into small pieces. Fourthly, drift complicates debris analysis. Fifthly, the flight data recorder underwater locator beacon stopped transmitting. Sixthly, the aircraft's path is still uncertain. And finally, the official search was suspended. So what is the most plausible final flight scenario? Investigators never reached a single definitive conclusion for the final minutes of Malaysia Airlines Flight 370. But based on satellite data, radar tracks, debris analysis, and the aircraft systems knowledge, one scenario is widely considered the most technically plausible by many investigators and analysts. Number one, the deliberate turnback after loss of communication. Number two, aircraft continues on autopilot for several hours. Number three, loss of consciousness in the cockpit. Number four, fuel exhaustion near the southern Indian Ocean. Number five, debris evidence supports a high energy impact. The ATSB search between 2014 and 2017 using the Fugro Discovery, Fugro Equator, Fugro Supporter, Go Phoenix, and the Donghai Ju 101. Ocean Infinity searched in 2018, 2025, and again this year using the seabed constructor, Armada 7806 and Armada 8605. The running total of the surface search, the bathymetric survey, and the underwater search is meanwhile 7.72 million square kilometers, which is the size of 80% of the USA, larger than Australia, and 80% larger than the European Union. A massive area has been examined, but the correct location has probably not yet been searched. Several analyses published after the main search ended suggested that the most likely crash location of MH370 may lie just outside the areas previously searched. These hypotheses combine satellite data from Inmarsat, debris drift modeling, and aircraft performance modeling. The first of these was from the ATSB, a primary search zone from 34 to 36 degrees south, but extending that out to 50 nautical miles. Second is the northern seventh arc hypothesis, around 32 degrees south. Thirdly, the Broken Ridge region from 28 down to 30 degrees south. And fourthly, the controlled glide scenario, 36 to 39 degrees south. What are the key flaws in these scenarios? Firstly, autopilot flight means a constant heading. That is incorrect. On a Boeing 777-200ER, the autopilot can follow multiple navigation modes. LNAV, which is lateral navigation, follows waypoints stored in the flight management system. Heading select flies a selected heading. Track select maintains a ground track. Direct to waypoint can change the flight route, and a manual waypoint can be entered anytime during the flight. The second flaw, there was no active pilot. That was actually never proven. The aircraft made structured navigation turns after diversion. Some analyses suggest altitude changes before reaching the seventh arc. Satellite BFO modeling does not uniquely determine altitude during cruise. The absence of an active pilot was an assumption, not a demonstrated fact. The third flaw, a recovery from a 15,000 feet per minute descent, is not possible. Sorry, but Boeing proved it is possible. And investigators asked Boeing to simulate the behavior of a Boeing 777 after dual engine flameout. In simplified terms, the model explored what happens when both engines stop, the autopilot disconnects, flight control computers remain powered by the ram air turbine, the RAT. The simulations reportedly produced two broad outcomes. In case A, an unstable descent in a spiral dive, and case B, an aerodynamic recovery. And both cases were supported by 5 out of 10 of the different studies. So in conclusion, I have 3 criticisms that are technically grounded. The autopilot does not mean straight flight. The absence of a pilot was not proven, and aerodynamic recovery from steep descent is possible. The search strategy relied on the most probable model, not the only possible model. The radar track across Malaysia shows multiple deliberate heading changes, structured navigation, and no evidence of uncontrolled flight. Some early analyses suggested unusual altitude changes. The available radar data cannot confirm those claims. Investigators therefore avoided drawing conclusions about altitude behavior during the diversion. The paper Bayesian Methods in the Search for MH370 by the Defense Science and Technology Group, DSTG, describes how probabilistic modeling was used to estimate the most likely crash locations of MH370. The approach used Bayesian inference, combining prior assumptions with available evidence from the satellite data, radar, and aircraft performance to produce a posterior probability distribution along the Inmarsat 7th arc. Let me list the key assumptions embedded in that framework. Number one, the aircraft followed a limited set of autopilot modes. Number two, no active pilot inputs after the Andaman Sea. Number three, aircraft speed was near long-range cruise. Number four, fuel exhaustion occurred near the 7th arc. Number five, satellite Doppler BFO data was reliable. Number six, the statistical prior from the civilian radar data and military radar data showed possible routes over Malaysia and the Malacca Strait. Number seven, impact occurred close to the 7th arc. Number eight, ocean drift was not used in the initial search definition. However, the search was refined with the Cicero drift data later on. So where was the pilot heading when he turned south? There are over 40 aeronautical and geographical waypoints when you leave the Kuala Lumpur flight information region near the first Inmarsat arc in a southerly direction. The implication from the DSTG analysis is that pilot was heading toward the geographical waypoint 38 degrees south, 88 degrees east, which is their most probable endpoint. And this DSTG flight path passes close to the aeronautical waypoints at Udam, Isbix, Mutmi, and Runnet. The DSTG flight path passes close to the geographical waypoints at 2 degrees north, 94 east, 6 degrees south, 93 degrees east, 13 degrees south, 92 degrees east, 20 south, 91 east, 27 south, 90 east, and 32 south, 89 east. Any one of these 10 waypoints could have been chosen, and if the autopilot reverted to a constant true track, the aircraft would have ended up in the DSTG-defined area. So was another turn, or even more than one turn, made in the 5.7 hours after turning south in the Andaman Sea? The data require a south turn, but not necessarily a turn-free southbound cruise. There were turns at the diversion near waypoint Igari, again near Kota Baru and waypoint Kadax, again near Penang and waypoint Angun. There was a turn south over the Andaman Sea, and all that within 1 hour and 20 minutes of the flight. The satellite measurements constrain where and roughly how the aircraft had to be moving at discrete times, but they do not continuously observe the aircraft between these times. Therefore, one or more additional autopilot-directed turns during the following 5-hour 42 minutes remain conceivable, especially if an active pilot was present and the guidance mode allowed waypoint diversion or recommanded track changes. Let me explain why MH370 will be found. The DSTG Bayesian analysis addressed the question, where is MH370 most likely to have ended up given the available information at the time? Their work produced a probability density function for the final location and provided the basis for the underwater search. Since then, approximately 260,000 square kilometers of seabed has been searched without locating the aircraft. The new information can be incorporated into the Bayesian framework as additional likelihood information, indicating that MH370 is unlikely to lie within the searched regions. The posterior distribution can therefore be updated accordingly. So where should we now look? DSTG defined the most likely search area given the data available in 2014 and 2015. Subsequent underwater searches have not located the aircraft, providing new evidence that can be incorporated into the Bayesian framework. In addition, sensitivity analysis of the aircraft trajectory model suggests that allowing additional maneuver hypotheses may broaden the set of feasible end locations. The purpose of my present work is therefore to update the Bayesian model to incorporate both the search results and the expanded trajectory hypotheses. So, what should the new search strategy look like? The DSTG analysis produced a probability density function for the final location of MH370. And that was based on the available satellite communications data and an aircraft trajectory dynamics model. This analysis provided the basis for defining the priority underwater search area. Since that time, approximately 260,000 square kilometers of seabed has been surveyed and searched, with high confidence detection probabilities exceeding 90% across most of the search region. In Bayesian terms, the absence of wreckage within these surveyed regions constitutes additional evidence that can be incorporated into the likelihood function. Updating the posterior distribution with this information reduces the probability mass within the searched area and correspondingly increases the probability in unsurveyed regions. The underwater search result is incorporated as a spatially varying detection likelihood, a term which is applied to the posterior crash location distribution. Regions searched with high confidence are down-weighted in proportion to their estimated probability of detection, while unsurveyed or poorly surveyed regions retain correspondingly higher posterior mass. In summary, the DSTG analysis has provided a rigorous Bayesian estimate of the most probable crash location based on the information available at that time. The absence of wreckage after extensive underwater searches provides new information that can be incorporated into the same Bayesian framework. Updating the model with these additional observations allows the posterior probability distribution for the final location of MH370 to be refined. Thank you very much for watching, and have a good day.